Hi, in today's video I would like to share with you a very nice problem of Bulgarian Mathematical Olympiad edition 1996, question number 1. Okay, here is the following setup. Find all primes p and q such that we have this product as 5 to the p minus 2 to the p is multiplied by 5 to the q minus 2 to the q all over this product p is multiplied by q. This whole number is an integer number. Okay, so in the other word, p and q is divide this product. In fact, this is nice problem which is more beneficial and containing more arithmetic rules. Okay, we can see a lot of tricks in this problem. Let's go ahead to make some notion about the arithmetic rules, including the Fermi Theorem. Here is the following rule for the Fermi Theorem. We have p is not divided a as an integer, equivalent we have a to the p congruent to the a mod p. This is general formula for the Fermi Theorem. If we divide both sides by a, you will get a to the p minus 1 congruent to 1 mod p. Let's go ahead and go into the solution. So let's find prime numbers such that this whole number p is multiplied by q is divided 5 to the p minus 2 to the p is multiplied by 5 to the q minus 2 to the q. Here is a problem because we don't have any information about this divisibility. We don't know p is dividing this term or this term. Okay, by symmetry reason, so either q is divide this one or this one. So I'm going to work on this one first, p, then by going through cases, because doing case by case to see p first. Again, I'm going to check p is dividing this one first for the first case. P is divide 5 to the p minus 2 to the p. It's equivalent according to the divisibility statement. That's mean 5 to the p minus 2 to the p equal to m is multiplied by the p, where m is some integers. In addition, 5 to the p minus 2 to the p congruent to 0 mod p. That's mean p is dividing this one. Okay, now we are ready to apply the Fermi Theorem here. So in this case we consider 5 is an integer, p is a prime by applying the Fermi Theorem. This is the component of two numbers here. So that's mean 5 to the p congruent to the 5 mod p by using the Fermi Theorem. Okay, the same thing with number 2 as a prime is congruent to the 2 mod p. Okay, or the same thing I can get by dividing both sides by 5 to the p minus 1 congruent to the 1 mod p. Same thing with the second statement, 2 to the p minus 1 by dividing both sides by 2 we'll get 1 mod p. So if I'm going to take this exponent off of this one, I'm taking the difference. So the same thing as this one equivalent implies 5 to minus 2 congruent to 0 mod p by applying the Fermi Theorem here. Okay, so this term equal to 3 congruent to 0 mod p. This one, that's mean p is divide 3. P as a prime dividing 3, that's mean p equal to 3. Okay, because there is no another choice for p, because p is dividing itself only, because p as a prime it cannot divide another number. So that's mean p equal to 3 implies p equal to 3. Okay, let's bring this important thing at the top and continue with our problem. I'm going to take this value and plug it into this expression. So I will have 5 to the 3 minus 2 to the 3 is multiplied by 5 to the q minus 2 to the q all over 3q. Okay, this is an integer. Now I'm going to calculate this term. If I'm calculating this term, it's giving me 117. Okay, 117 is the same thing as 3 is multiplied by 29. Okay, 29 is the same thing as 13 is multiplied by 3. Okay, now I'm going to cancel out number 3 from numerator and denominator, so I will be left with 3 is multiplied by 13 is multiplied by this product 5 to the q minus 2 to the q is divided by q. So now, since this one is an integer, that's mean q you will divide 3 or q divide 13 or divide this one. Okay, so we will have the following solutions. Okay, so I'm going to give the solutions for this one, then we prove second case. Okay, because this case only we have p is dividing this one. We are going to check again in the second case p is dividing this one to see if it's given us the same solution. That's mean the only solution available which we will have. Okay, so now the first solution for p and q, we will have 3 and 3 because we already found 3, and this q divide 3. Okay, in order to have this one as an integer. So the second solution is 3 and 13. Okay, in order to have q dividing 13, that's mean q will be equal to 13 because both of them are primes. Q must be equal to 13. So now we are going to check with this one. We don't know this one yet. If you take a look at this term we already proved it with p. We found 3. Okay, as you apply in the Fermenter Theorem, similar to the previous one. So we are going to work on this one. Don't forget we have pq as a symmetry solutions. So this one you will have 13 and 3 again because for the symmetry reason. Let's consider the second case to check p is dividing this term. Okay, now in this step I'm going to consider the case when we have p is divide 5 to the q minus 2 to the q. Okay, previously we saw p is dividing 5 to the p minus 2 to the p. Now in this case we are going to see p is dividing this term 5 to the q minus 2 to the q. Okay, this one equivalent 5 to the q minus 2 to the q congruent to 0 mod p. So in this case we are going to see the GCD of p minus 1 and q strictly superior than 1, and GCD of these two numbers of the p minus 1 q equal to 1. Okay, since we are going through the GCD, so we have two cases. This case is rarely available to find two primes are equal. Okay, to give you the GCD is greater than 1. Okay, if p equal to 3 and q equal to 2, if p equal to 3 you replace 3 minus 1 which is 2 and q is 2. That's mean the GCD of these two numbers is not 1 because we have number 2 as a common divisor of this one. Okay, so that's mean GCD is superior or equal to 2. Okay, so this one is not available because when you replace 3 with p here and q with number 2, this one become not integer. Okay, we are going to work on this one now. So we must go through these cases because to show up everything, because sometimes you may find the problem if you skip this case, you will find a problem. We have to go through this GC. So now let's move on to this one now, GCD. So in this case, we are going to have a linear combination operator for these two terms. So GCD. So there is some natural number a and b, such that we have the E is multiplied by Q minus B is multiplied by P minus 1 equal to 1. I put minus sign between these two terms because we have chosen these numbers as positive numbers. This is our choice, okay? I'm controlling the sign of these numbers because this is my choice, okay? You can put minus or plus. If you put the plus, you can have chosen all the numbers, including the negative numbers, okay? So now, depends what you need, okay? So this is equivalent e to the q equal to b is multiplied by p minus 1 plus 1 by taking these two terms to the other side of this equation. So I will have this nice equation as a Bezout theorem, okay? I have these two terms, 5 to the q minus 2 to the q is congruent to 0 mod p. I'm going to raise a as an exponent here. It's equivalent 5 to the aq minus 2 to the aq congruent to 0 mod p, okay? So what I'm going to do now, I'm going to replace aq with this equation, okay? I will have 5 to the b p minus 1 plus 1 minus 2 to the b to the p minus 1 plus 1, okay? Congruent to 0 mod p. Now I'm going to simplify this one. I'm going to simplify this exponent. I will have 5 is multiplied by 5 p minus 1 to the q. Just I'm following the exponent rule here. Minus 2 is multiplied by 2 to the p minus 1 is multiplied by q congruent to 0 mod p, okay? If you apply the Fermi Theorem, this term 5 to p minus 1 is a congruent to 1 mod p. The same thing here, this one is a congruent to the 1 mod p, okay? Since p is not divided 5, now we are allowed to apply the Fermi Theorem here, okay? I'm taking off all of these things. So this one equal to 1 mod p. By applying the Fermi Theorem, this one equivalent 5 minus 2 congruent to 0 mod p, okay? So after simplification, we will have 5 minus 2 congruent to 0 mod p. This one equal to 3. This one equal to 3. So that's mean p divide 3, okay? Since 3 congruent to 0 mod p, that's mean p divide 3. So p divide 3, so that's mean p equal to 3. So the only solution that we have, this one which we found before, so p is equal to 3. By symmetry reason, so the whole job that we have done, it will be the same thing with the q by symmetry, okay? So you will have the solutions 3, 3, 3, 13, 13, 3. So I have common solution here 3, 3 and 3, 13, 13, 3 by symmetry, okay? So I have done with this problem. If you have any question or suggestion, just put it in the comment section below. If you are interested in watching this one, just don't forget to support us with your like and subscribe. Thank you for watching. I will see you in next video. Bye.